Welcome to Math 389 Advanced Analysis. This is lecture 22. And so today we're going to prove the fundamental theorem of calculus. And depending on what people are interested in, that will impact what level of assumptions we're going to make. The more assumptions you make, the easier the proof becomes. And so what I want to do is, here is your version on the web. The way I like to phrase it is, we have some function, little f, big F is an antiderivative, and we define the integral from a to b of f of x dx to be the area under the curve from x equals a to x equals b. And then the fundamental theorem of calculus, the content is the area under the curve is the antiderivative at b minus the antiderivative at a. So it's a nice result that if you have two functions that have the same derivative, they differ by a constant. That's why we don't have to specify which antiderivative we look at. And so what we'll do is we'll first prove that, then we will reduce the fundamental theorem of calculus to a certain calculation, and then we will see what do we need to assume in order to prove that calculation. So the first, I guess, is we'll start with lemma 1. If big F prime of x equals big G prime of x, then f of x minus g of x is constant. This is one of the no-shit theorems, right? If I have two objects and their speed is the same at every moment in time, then the distance between them must be constant. So the question is, how do you prove this rigorously? So proof. So we can let a of x be f of x minus g of x. And note, we have a prime of x equals 0 for all x. So why does a prime of x equals 0 for all x imply a is constant? So remember, if we take the function little f of x is e to the negative 1 over x squared, if x is not 0, 0 if x equals 0, it has a Taylor series that's identically 0, but the function is not identically 0. So the difference is, when we look at that function, we're looking at something that's going on at one point. Whereas now we're looking at something that is 0 everywhere. So how would you rigorously prove that if you have a function that's identically 0, I'm sorry, a function whose derivative is identically 0, the function must be constant? Okay, so how do you get the contradiction? Assume the function is not constant. Good. So one thing is good. So assume a is not constant. So let's say, without loss of generality, we could say a of 0 does not equal a of 1. I can always just rescale and adjust, so I have 2 points. So here's 0, here's 1. I can always, adjust it as well if I want, so I could assume a0 is 0 and a1 as well, but it doesn't matter. We'll have 2 different values.
Can we use mean value theorem?
Yes. So mean value theorem would be great now. So by the mean value theorem, f of 1 minus f of 0 is going to be f prime at some intermediate point c times 1 minus 0. But what do we know about f prime of c? 0. Therefore, f of 1, I guess I'm using the letter A, not F, sorry. Cannot do a search and replace with writing. So A of 1 minus A of 0, A prime of C, so we get A of 1 equals A of 0. And in fact, do we really need to say that there are 2 points where they're different? No, it's not bad to do that. I mean, that's my natural go-to. Let me say that there's 2 points. Let me talk about what's going on. But we could just go direct. By mean value theorem, I keep doing it. A of B minus A of A equals A prime of C times B minus A equals 0. Therefore, A of B equals A of A. So all the same. I'm sorry, wait a minute. Wait a minute, did we just make a mistake? Oh yeah. So this proves that A is constant, yes. So our function has to be constant. So this is really good. So when we're looking at the fundamental theme of calculus, we can use any antiderivative. Okay. So now, lemma 2. Well, let's talk about partitions first. So without loss of generality, the world lives between 0 and 1. And typically we partition things by equal slices. I mean, this would be x0, this would be x1 is 1 over n, this would be xk is k over n, this would be xk plus 1, which would be k plus 1 over n, and then this would be xn, which would be n over n. And again, I don't have to live on the interval 0, 1, I could live anywhere I want, but this just makes things nice. In some things, like if you're solving differential equations, you may not want to choose all the partition points to be the same. When you're doing these numerical approximations, if your first derivative is really small, you don't want to be taking a lot of points there because it's not really changing. You want to use your computational time in the places where it's changing greatly. So this would be like a dynamic allocation of, but for theory, let's just take them all to be the same. And we can try to estimate the area under the curve. So if I give you some function, here's y equals f of x, I could then look and see what is the area under the curve from xk to xk plus 1. Okay. And then if the function is nice, the hope is that if we can approximate this well, the more partition points we take, the better the approximation will be and it will converge. And so what we'd love to do is we have, say, the interval xk plus 1, which is, k over n to k plus 1 over n. Assume there exists points lk, uk such that f of uk, let's do lk first. F of lk is less than equal to f of x less than equal to f of uk for all x in this interval ik. So we'll call this interval ik. Then f of lk times 1 over n, which is the area of the low approximation, would be less than equal to the area under the curve from xk to xk plus 1, that's our notation, would be less than equal to f of uk times 1 over n. So this is a slightly delicate point. How do you know your function has a smallest and largest value on the interval? So, you guys have been in high school more recently than I. When you did this in high school, did they argue along these lines for upper sums and lower sums? Did they say that these points UK and LK exist?
They asserted that.
Right, and how do we know they exist? So how do you know there's such a point? Okay, so in high school, did you prove a continuous function on a closed bounded set attains in high school? If you did that in high school, please contact your high school teacher and say they've impressed me. That's the first time I've heard that from a high school student. Okay, did anybody else have that actually proved in high school? No. What do we need to prove that? What subject? Analysis. So typically in analysis, we would then show that on a closed bounded set, you attain its maximum and minimum. If not, we have to put that in as an extra assumption. If our functions are nice, this is not a big assumption. Which functions would be nice?
Ones that don't blow up.
Well, but you'd still have to prove that. There's a certain class of functions that are nice. So real analysis shows we have UK and LK. If our function is blank, then have them.
We'll have them if it's bounded, but that might be too narrow.
But how? You'd have to prove it.
Is it just Riemann integral?
You'd have to prove it. You need to prove that there is an upper and a lower value.
Oh, then we can just assume it's bounded then. Right.
But you still need to know that there's some point LK and some point UK.
Extreme value theorem.
And how do you prove the extreme value theorem?
Continuous?
Yeah, continuity.
Yeah, but you have to start using some continuity, maybe uniform continuity, maybe compactness. There's a certain class of functions where we know we have it. Anybody have any thoughts as to which functions is this going to be trivial to prove there's an LK and a UK?
Constants.
Constants, but more general than constants.
Polynomial? Oh. Step function?
I'm sorry?
Step function?
Step function, linear function, what else? So I want the largest class. Monotone. One of my friends once expanded WLOG without loss of generosity. If the function is monotone, that means it's either non-increasing or non-decreasing. And then you know the values are at the far left and the far right. So if I give you a function that's monotone, or if I give you a function that's monotone on regions, I could split it up. If I give you a function that's a sum of monotone functions, so I can't handle the polynomial, say, 1 minus x plus x squared. But I could handle 1, negative x, and x squared individually and then combine them by linearity. So if I take functions that are monotone, we're okay.
Yeah, really? What if it blows up?
Okay, so I am assuming my functions are continuous, yes, yeah. But again, it's trying to get a sense of what do we need to prove this in great generality? And we need to know some results from real analysis. We need extreme value theorem that any continuous function on a closed bounded set attains its maximum and attains its minimum. If we assume the function is monotone, then we have the result for free. It's trivial. It's either starting small and getting large or starting large and getting small. But again, it's worth keeping track of just what do we need to assume. So we will assume function is monotone for now, or sum of monotone. Okay. Okay. So now we have the upper and lower sums. And now lemma 2, if f is nice, the limit as n goes to infinity of the lowest sum equals the limit as n goes to infinity of the upper sum. where the lowest sum is the sum of f of LK 1 over n. K goes from,
Sorry, I think we need more than continuity, right? For example, like a log function. It's continuous on its domain.
as long as the function is continuous, then real analysis kicks in. If the function is continuous on a finite, closed bounded interval, then it attains its maximum and
Or
minimum.
we has to get a compact interval, like an extreme value theorem.
Well, the fact that okay.
So log is on an open
Yeah,
interval.
yeah,
Right.
it is on open, yeah.
Right, so log blows up, so log would not be. And so the lowest sum and the upper sum would be defined as, I'll go from 1 to n. So this is the next lemma. If f is nice, and we have to figure out what is nice, then we know the upper sum and the lowest sums converge. Do they converge monotonically? Do the lowest sums ever get smaller? Do the upper sums ever get larger as you take more points? So is L of n plus 1 greater than or equal to L of n, and U of n plus 1 less than or equal to U of n? So as we take more partition points, could the lowest sum become smaller? Could the upper sum become larger? And it might still converge, but maybe we take a step backwards. So it's what direction are we converging? Are we converging in such a way that as I increase n, it's not getting worse?
It's all up to it's like closer approximating. The function,
So one of the points of today's lecture is to just demonstrate just how careful you have to be on statements. It could depend on how things wrap around, because if we go from 4 points to 5 points, depending on where the function is largest, that could change from being in one interval to another. And so the answer is not necessarily. As a nice exercise, find an example of a function in a partition where when we added one more point, the lowest sum went down or the upper sum went up. Sometimes people do dyadic decompositions. If you do powers of 2, that's going to really make things much better in terms of how things will go, because then you're splitting things in half. So this avoids complications. We don't need to know that it's converging in a certain direction. We just need to know that the limits are converging to a common value. It's okay if occasionally you have to go back a little bit. So let's look at, so we'll investigate the sum, k goes from 1 to n, of the upper sum, FUK 1 over n, minus the sum, k goes from 1 to n, of the lower sum, f of LK 1 over n. Has anybody ever seen the TV show Friends?
Yes.
I think except for 2 episodes, every episode begins, or its title begins the same way.
Oh, really?
Yes. How are the episodes of Friends titled?
I thought it's just Friends.
I'm
No.
sorry?
Is it not just Friends?
But each episode has a name. Like
Oh.
one of the worst.
I actually never pay attention to
episodes
the
of Doctor
title
Who is
of each
blank.
episode.
episode 1, episode 2, episode
So I think episode 1 might be just called the pilot.
Oh,
And the final one might have a different, might be just the finale. But every other episode begins with 3 words. Begins the one
Keep
with.
one with.
The one with, the one with, the one with. This lecture, if it was being made into an episode of Friends, would be the one with the mean value theorem. When in doubt, use the mean value theorem. The mean value theorem is a great stepping stone approximation to Taylor's theorem, but you need a lot less in terms of proving it. We've already used the mean value theorem once today, right? When we said that if you have speed 0, you're not proving. Okay. So when in doubt, what should you use? Mean value theorem. So what do you think we should use to analyze this quantity? What would you try? Yeah, let's try the mean value theorem, right? So this is the same as the sum, k goes from 1 to n, of f of uk minus f of lk times 1 over n. Now, if we use the mean value theorem, what can we say about this? So what can we say about f of uk minus f of lk? You want to use the mean value theorem, so what can you say about it?
so like it's less or equal to like, or sorry, it's equal to like f prime c times uk minus lk, where c is between lk.
Okay, good. So if we look at the absolute value of un minus ln, this is going to be less than equal to the sum, k goes from 1 to n, f prime at some point ck, absolute value, uk minus lk, absolute value, 1 over n, where ck is between lk and uk. Now, if I look at the left-hand side over here, I know this quantity has to be non-negative because it's the upper sum minus the lower sum, right? Is everybody comfortable that the upper sum minus the lower sum can't be negative? So I don't really need the absolute value on the left. But when I start using the mean value theorem, I have to be careful because I don't know which comes first, LK or UK. And it's possible maybe f prime of c is negative. So I've got to be a little bit careful. How large can UK minus LK be? So maybe here's xk is 1 over n. Here's maybe xk plus 1 is k plus 1 over n. Maybe this is lk, and maybe this is uk. What's the greatest distance between lk and uk? 1 over n. So note, uk minus lk is at most 1 over n. So our upper sum minus the lower sum is going to be less than equal to the sum, k goes from 1 to n, of f prime of ck, 1 over n, 1 over n. So this is going to be less than equal to 1 over n squared times n times the maximum of f prime of x in absolute value. Right? So if the maximum of f prime is finite, this goes to 0. because I'm dividing by n. So it looks like the upper sum and the lower sum converge to a common value. What did I need to assume? I needed to assume my function f is not only differentiable, but bounded. So let's collect assumptions to date. Collect assumptions to date. So what was the first thing we assumed? So we assumed f is monotone or sum of monotone pieces, or piecewise monotone. Okay. For the standard functions we're going to look at, that's not a big deal. If I give you something, the sine of 1 over, x sine 1 over x, that now becomes a big deal. Right? So what was the second? Is f prime exists and is bounded. So that was our second assumption. Do we agree with this so far? Okay, so far, if we assume we have these properties, then the upper sum and the lower sum converge. These properties are not hard to prove if we use some results from real analysis, we use uniform continuity and all those wonderful, wonderful results. But most of us did not have a good high school where we did stuff like that. So for most of us, we have to be a little bit careful. All right, I think we're on lemma 3. All right, lemma 3. If f is nice, the upper sum of n and the lower sum of n converge to the area. Does that seem reasonable?
By nice, you just need a condition you've already set.
Yes,
on it.
yes. So the main thing is, and the question is, do we do this in enough detail? Over here, oops. This is the true area. And we have the true area is sandwiched between the upper and the lower sum approximation. So if we sum all of those, then that should give us bounds. So is everybody comfortable that the true area is somewhere between the upper sum and the lower sum? All right, I'm going to do proof by picture. Okay. I just don't get to draw Mickey Mouse that often. Okay. So here, let's prove it vigorously. Proof. Here's Ln less than equal to the true area less than equal to Un. And we know as n goes to infinity, Ln and Un converge. Or do we know they converge? We know the distance between them converges to something. It gets small and small and small. So does that imply that Ln and Un have to converge to a common value?
If the distance between them converge. Yeah, I mean, that's our limits are the same. That's number 2. Well, it means that at the limit Un minus Ln is 0, right? Yeah. Is that what you mean by distance?
So do they converge to a common value? What do you want to call that common value? A. And you're choosing A for area, right? So if the upper sum and the lower sum converge to a common value, and the true area lives between them, what's the only thing the true area can converge to? Yeah. And so the upper sum and the lower sum have to converge to the true area. You have to be a little bit careful. Imagine, I'm not taking the Lagrangian, imagine Ln is equal to the lowest sum plus n, and U of n is equal to the upper sum plus n. What is true about script un minus script L of n? That's just un minus ln, and that goes to 0. So the difference is converging to 0, but un and ln diverge. They don't converge to a common value. The whole point of today is to just really drive home how careful you have to be about everything. So do you agree I have a situation where I have two functions? The difference between them is going to 0, but neither function converges to anything. So why is that not a problem here?
They're not like both increasing or both decreasing.
Why is that not a problem here?
Like both UN and LN converge.
Why do we know they converge? But we don't know that ln and un are monotone.
They have a monotone subsequence.
And we can choose the partitions.
So one thing is we could play the game of looking at partitions where the number of points is powers of 2. And then if we do something like that, then we can get monotone. Because then what we're doing is we're taking an interval and we're splitting the interval. And when we split the interval, then the lower value of the whole interval, we're then going to compare with the lower value of the two subsplits. And then we're going to be fine. So then we would know that we have some kind of monotone, and now we can use some results from real analysis. If you have a sequence that's increased, that's non-decreasing and bounded, it converges. Right? But just try to get a sense of what do we need to actually make this rigorous. We also know that ln is bounded by the true area. And we know un is bounded below by the true area. So imagine that ln does not converge to the true area and un does not converge, or at least one of them doesn't converge to the true area.
That would be a contradiction with third of the speakers.
Right, so how do we do this rigorously? So we have ln less than equal to true area less than equal to un. Imagine ln does not converge to the true area. Then there exists infinitely many n and an epsilon greater than 0 such that ln is less than equal to the true area minus epsilon. So there exists infinitely many n such that un minus ln is greater than or equal to epsilon. Contradiction. So again, they sometimes say once in your life you should see something done in full glory. Or maybe it's glory, I'm not sure. But you should see it at least once and just be aware of how careful do you need to be. One of my favorite or least favorite moments as a professor at Williams was when I was teaching complex analysis. I might have shared this, and I wanted to do like the branch cut method or something like that. And there was a standard bound that I needed to do. And so I was just going to say, and by the standard argument one has, and I realized it's standard to me because I've been doing this for 2 decades. For somebody who's seen this for the first time, it's not a standard argument. And you have to go through and you have to do the details. When you're starting out, you have to be careful. You have to dot every I. As you get older, you become very careless and lazy. And you hopefully have a good intuition of when do you need to be careful. And hopefully you are always careful when you need to be. So we do know here that there's an upper and a lower sums. We know that they're on different sides of the true area. And so if one of them didn't converge, then there would be a separation. We know that doesn't happen. So can have, ln monotonically increasing, or I guess non-decreasing, if do n equals 2 to the k. And then similarly for the upper sums. And again, the reason that's true is if here's, xk plus 1, and now I break it in half. If this was my function, if this was the smallest value before, then if I look at the other half, I can't have it having a smaller value than the global small. The global small is on one of the two halves, and the other one either has that as its global small, as its small as well, or it has something larger. So the lower sum can't be getting smaller. So is everybody comfortable on this level of detail? We're getting close. We've already proved 3 lemmas. So we've shown that we can use any antiderivative. That's great. We've shown that we have upper and lower sums, and that they converge as long as f is nice. And for us, f is nice as if it has first derivative that's bounded. And I guess implicit in saying the first derivative is bounded is the first derivative exists. And then we are assuming that our function f is monotone, or is the sum of monotone pieces. And then that one's a little problematic. We might want to look at something like, x sine of 1 over x. Okay. So we know that the lower sums and the upper sums converge to the true area. So all we have to do is compute what is the lower sum or the upper sum, right? And if we can compute that and show that it's the antiderivative of b minus the antiderivative of a, we're done. All right, so now, oops, wrong way. What do you think lemma 4 is going to be? Show what is equal, so the difference between the antiderivatives. So show what?
Either U of N or L of N.
Right, since you're speaking, you get to choose. Do you want to do up? Do you want to do upper or lower? Oh yeah, good. Yeah. So show that the limit as n goes to infinity of the upper sum is f of 1, big F of 1 minus big F of 0. Because we've just normalized things that way. So proof. So the upper sum of n is the sum, k goes from 0, I think we're doing from 1 to n of f of u, f of uk times 1 over n. And we want to show that this is equal to, as n goes to infinity, big F of 1 minus big F of 0. What should we use? What are your thoughts? Yeah, I was trying to get it to play the Friends theme song, but it's not playing. Although I'm not sure if legally I'm allowed to play the Friends theme song. But we should use the mean value thing. So part of it is you've got into some really lazy habits over the years. If you're going to tell me use the mean value theorem, you're not giving me enough information. What information do you have to give me? Use the mean value theorem. Be more specific. What am I using the mean value theorem on? What do you have to tell me if I'm going to use the mean value theorem? You have to give me what? I'm sorry? Okay, so to use mean value theorem, need two values, and what else? And a differentiable function. Right? If I'm going to use the mean value theorem, I need a differentiable function. Any thoughts about what we should choose for a differentiable function? Big F. So there's only two possibilities, big F and little f. We are assuming little f is differentiable, so it's possible. Don't worry, we'll apply the mean value theorem to little f, I'm sure, in a few moments. So let's take our function is big F. What are our points? We could do 0 and 1. But that would only give us, huge, just big, giant interval. What would be better than doing all of 0 and 1? Yeah. Function is f, and then a is xk, and b is xk plus 1. So then that gives us big F of xk plus 1 minus big F of xk is big F prime at some point, let's call it ck, times xk plus 1 minus xk, where ck lives in the interval xk to xk plus 1. But what is xk plus 1 minus xk? 1 over n. And f prime, big F prime is just little f. So we get big F of xk plus 1 minus big F of xk is equal to f little f at ck times 1 over n. And then let's just sum both sides and go, k goes from 1 to n. What's the sum on the left? This is f2 minus f1 plus f3 minus f2 plus f4 minus, oh, I'm sorry. The way I'm doing things, I want to go from 0 to n minus 1. Oh, wait a minute. Rather than erasing all of those, it's just better to write it as f1 minus f0. That's faster. So I'm going to have k goes from 0 to n minus 1. Whoops. F3 dot dot dot. And then the last one, oh, sorry, shoot. Yeah, they should all be over n's.
Not too bad. Just because like F1 goes to
And it goes all the way down to f of n over n minus f of n minus 1 over n. And what you see is basically everything cancels but the extremes. And this is going to just equal big F of 1 minus big F of 0. And that's going to be the sum, k goes from 0 to n minus 1 of fck 1 over n. Is that the upper sum?
technically since you know what CK is.
So we don't know what ck is. So we're close. we have the sum, k goes from 0 to n minus 1 of f of ck 1 over n is big F of 1 minus big F of 0. And then the upper sum is the sum. I'm going to re-index. Is that okay with everybody? It's going to be the sum of f of uk 1 over n. Right? I want to show that these are basically the same in the limit. So here we have f of 1 minus f of 0, which equals the sum k goes from 0 to n minus 1 of f of ck 1 over n. Over here, we have the sum k goes from 0 to n minus 1 of f of uk 1 over n. This is our un. And similarly, we would have the sum k goes from 0 to n minus 1 f of lk 1 over n. Well, the upper sum, why is that true? Why is the upper sum at least as large as the boxed quantity?
Is the boundaries are the same, but 1 over n term is the same, and f of uk is by definition greater or equal to.
Good. By definition of the point, that's where the function is largest on the interval. So as f is largest on ik at uk, f of uk has to be at least as large as f of ck. So we know the upper sum is at least as large as this quantity. We know the lower sum is at least as large as this quantity. And we know that the upper and the lower sums converge to the true area, right? If they converge to the true area and this quantity is always between them, what's the only thing that's left for that quantity? It has to be the true area. Right? I know the lower sums and the upper sums, they're converging to some quantity. If it's not the true area, and this is always between them, then there's a separation between this and the true area. We could also try to look at things directly and look at the difference between the upper sum and this quantity in the box. What could we use to look at the difference between those? Okay. Okay. And so how would you prove that rigorously?
Like the same argument.
Liberty Mutual.
No, it's not Liberty Mutual. The mean value theorem. Right? It's the mean value theorem. When in doubt, use the mean value theorem. Right? So if you look at this, we can look at f of uk 1 over n minus f of ck 1 over n, and then sum that k goes from 0 to n minus 1. That's going to be the sum k goes from 0 to n minus 1 of f prime. We need a new letter. I'll use gamma. Gamma k 1 over n. Oh, sorry, gamma k, and then it's going to be uk minus lk times 1 over n. So if we take the absolute value of the sum k goes from 0 to n minus 1, f of uk 1 over n minus f of ck 1 over n, that's going to be less than equal to the sum k goes from 0 to n minus 1 f prime of gamma k how large can this be in absolute value? I'm sorry? No, I think you're right. How large can it be in absolute value? Sorry? 1 over n times 1 over n squared. So this is going to be less than or equal to 1 over n squared times n times the maximum value of f prime of x in absolute value. So if f prime exists and is bounded, above goes to 0. So as soon as we start to assume that f prime exists and is bounded, a lot of these calculations become really nice. So what we have here, there's a name for such a sum. Does anybody remember the name for the sum? Telescoping. So only the first and the last piece matter. And so this is the proof of the fundamental theorem of calculus. We then tested it, last time. Just for completeness, you test. Take f of x equals 1, x can do. But these are just rectangles and triangles. It's really not that impressive to find the area, right? I'll just do 0 and 1. So in that case, you get, f of x equals 1, big F of x equals f. Area is 1 times 1 equals 1. Big F of 1 minus big F of 0 is just 1. If we do the triangle from 0 to 1, f of x now is x. Big F of x, we can take it to be 1/2 x squared. Area is 1/2 base times height, so it's 1/2. And then big F of 1 minus big F of 0 is just 1/2. So if we do this, yeah, we get the result, but these aren't really that hard shapes. So the first non-trivial test is if we take f of x equals x squared. And I believe the ancient Greeks did have the formula for the area under a parabola. And so we want to now find what that is. So if we calculate the upper sum, that's going to be like the sum k goes from 0 to n minus 1, f of xk 1 over n. So this is the sum k goes from 0 to n minus 1. I'm sorry, it's not xk, it's uk for the upper value. But on each interval, where does the function take its largest value? I'm sorry?
Largest part.
Yeah, so this is really now just the same as k goes from 1 to n, f of xk 1 over n, as largest at right endpoints. So then this is the sum k goes from 1 to n. xk is k over n. I square that and multiply by 1 over n. So this is 1 over n cubed, the sum k goes from 1 to n of k squared. What does that sum equal?
Set of squares, so it's n times n minus 1.
Nope.
Minus 3.
Nope.
2.
Nope.
N plus 1.
n plus 1 over 6, 2n plus 1. So this is I'll write it this way. It's 1 over n cubed times 2n cubed over 6 plus something of size n squared plus size n plus size 1. I don't really care what the other stuff is. this is going to be 1/3 plus something of size 1/n plus size of 1/n squared plus size of 1/n cubed. So as n goes to infinity, get 1/3. Well, what's the antiderivative? It's 1/3 x cubed, which is big F of 1 minus big F of 0. So that's a non-trivial verification of the fundamental theorem of calculus. We've now found the area under a parabola. And can you do this without induction? I think the Greeks did get this. Can you find the area under the circle without using the fundamental theorem of calculus? Can you get the upper and the lower sums to work? The function's monotonic, the function's differentiable. Good luck, right? This is the power of the fundamental theorem of calculus. We don't have to go through and do these upper and lower sums. If I give you here's my function. F of x is the square root of 1 minus x squared. I want you to do the limit as n goes to infinity, the sum, and k goes from 0 to n minus 1 of, say, f of uk 1/n. Good luck doing that. Here's a nice corollary. We've already used so many letters. WK be any sequence of points with, say, WK and IK. And the limit as n goes to infinity of the sum k goes from 0 to n minus 1 of f of WK 1/n is equal to the area. Really, maybe I should have WK comma n to remind myself that these points are coming from the subdivision of n pieces. I'm hoping the notation is clear. What this is saying is take any sequence you want. And the reason is the lowest sum is going to be less than or equal to the sum k goes from 0 to n minus 1 of f of WK 1/n is less than or equal to the upper sum. And since the lower and the upper sums converge to the true area, this has to converge to the true area. It's the sandwich there. So this is the fundamental theorem of calculus. What assumptions did we make? Basically, we're assuming that our function is either monotone or the sum of monotone. We're assuming our function is differentiable. And we're assuming that the derivative is bounded. Any function you are doing with almost any high school class will satisfy those assumptions. They're not big asks. But you can remove them. And you can then start to do things such as uniform continuity. So, oops. Somehow I got an extreme close-up. Okay, there we go. And that extreme close-up now, that becomes just a little bit. So can bypass assumptions on F with uniform continuity. So what's the definition of uniform continuity? So uniform continuity on, let's say, the interval 0, 1. Can anybody give me the definition? What's the definition of continuity? So what does it mean for function f to be continuous? So f is continuous at x if
Well, the formula is if you can zoom in as much as you want on any point of the function, then you will still see the function. Formula that's going
wait, say it again.
if take a function of the interval, you
Right.
zoom into any point of
Yes.
the function, and however much you want to zoom in, you'll still see the function. Will be in your
So there's no gaps.
vision fields.
Okay, we need to make it math speak.
So
If for all epsilon greater than 0, there exists the delta, which can be a function of epsilon and x, such that for all y with the absolute value of y minus x less than delta, then f of x minus f of y is less than epsilon. So you give me any tolerance, and I can tell you if you zoom in this much, you won't go outside. Okay? So see below for uniform continuity, but now delta just depends on epsilon. That's what uniform continuity is. That you can choose one delta that works everywhere. And then I've never taught real analysis, so it takes me a while to remember all this. I think you use some kind of open cover. If I have a compact set, I can cover it with if I cover it with a set of open sets, then a finite subcover exists.
Yeah.
And for each x and 0, 1, you give me an epsilon, I construct a ball of radius delta epsilon x about that. Those balls will cover, I then take a finite subcover of those, I take the smallest delta, and that gives me my uniform continuity. So we can prove a continuous function on a closed bounded interval is uniformly continuous. So consequence, a continuous function on closed bounded interval is uniformly continuous. And then you want to show that if you're uniformly continuous, then the upper sum and the lower sums converge to a common value. So is that lemma 2? I think.
Yeah.
So now, lemma 2, uniform continuity implies the upper sum minus the lower sum goes to 0. And the proof is the upper sum minus the lower sum, I'll put in the absolute value because I like it, is this, let's see, go to the sum, k goes from 0 to n minus 1 of f of uk minus f of lk, absolute value 1 over n. I don't need the absolute values, I just like putting them. What we know, uk minus lk is less than or equal to 1 over n in absolute value. So we know the points uk and lk are close. So by uniform continuity, for all epsilon, there exists a delta such that if x minus y is less than delta, then f of x minus f of y is less than epsilon. So now what we can do is you give me an epsilon, so given epsilon, choose n so large that 1 over n is less than delta. Then the absolute value of f of uk minus f of lk is less than epsilon. So the difference between un and ln is less than or equal to epsilon times 1 over n times n, because all the summands are now bounded by epsilon. And that's just epsilon, which I can send to 0. So if we have uniform continuity, then it's actually not that bad to show that the upper and the lower sums converge. And so you can similarly see that a lot of the, we don't really need to assume anything about f being differentiable. But it's worth considering, what would you do if I gave you this function? I always want to make sure I do it correctly. F of x is x cubed sine of 1 over x. G of x is x sine of 1 over x. And this is if x is 0, this is if x is not 0. Are these functions continuous? Yeah, for the first one, sine will be like this. And because I have the x cubed and the sine of 1 over x, it's going to be, oscillating, very, very rapidly. But what you can do is you can get some kind of bounds near the origin. So near the origin, it's going to look something like this. And then we take the negative of that. And so what we're going to have is going to be something coming in like that. And then the same on the other side, just really poorly drawn. The first function is differentiable, the second one is not. And good luck trying to calculate areas under curves directly. You could approximate it by using Taylor series and whatnot, but anyways, I hope this was interesting. It's at least something you should see in rigor. How similar is this to what you did in high school?
Pretty similar. I think what we did is in the Lemma 2, we used the extreme value theorem and just said when you're integrating, you're always doing it on a closed set.
Right, but you then need the extreme value theorem.
Yeah.
And how did you prove the extreme value theorem? Do you remember?
I don't remember, but it was taught in an analysis way because his philosophy towards teaching the class is that you can learn the material for BC calculus in like the equivalent of 3 lectures.
Yes.
So he was going through the curriculum and teaching it like an analysis.
Yeah, I mean, when I teach multi, I tell people I can teach you, essentially half the class partial differentiation in under a minute. Yeah, and I have somebody time me, says, just pretend y is constant. Done. And that's essentially partial. I mean, that's essentially partial differentiation. Now you have to prove some results. Just because the partials exist doesn't mean that the function is differentiable. But that's often glossed over. So the real question is, what do we need to make all of this work? All right, so this is a good place to stop.